Neural networks are a fascinating area of computer science. They are designed to mimic the way our brains work. Just like our brains learn from experience, neural networks learn from data. They can adapt and improve their performance over time. This makes them incredibly powerful tools for solving complex problems. Imagine a computer program that can learn to recognize objects in images, or a system that can translate languages with remarkable accuracy. These are just a few examples of what neural networks can achieve. Neural networks are already having a significant impact on our lives. They are used in a wide range of applications, from self-driving cars to medical diagnosis. And as research in this field continues to advance, we can expect even more groundbreaking applications in the years to come. To understand how neural networks work, it's helpful to think of them as a network of interconnected nodes, much like the neurons in our brains. These nodes are organized in layers. The input layer receives information from the outside world, such as an image or a piece of text. This information is then passed through one or more hidden layers, where complex calculations are performed. Each connection between nodes has a weight associated with it, which determines the strength of the connection. Finally, the output layer produces the network's prediction or decision. For example, if the network is designed to classify images, the output layer might indicate the probability that the input image belongs to a particular category. Each node receives input signals from other neurons and combines them. This combined signal is then transformed by an activation function. This function determines whether the neuron should fire, that is, transmit a signal to other neurons. One of the most remarkable things about neural networks is their ability to learn from data. This learning process is called training. During training, a neural network is presented with a large data set of examples. For example, if we want to train a network to recognize cats in images, we would show it thousands of images of cats and non-cats. Each image would be labeled with the correct answer, cat or not cat. The network then adjusts the weights of its connections to minimize the difference between its predictions and the correct answers. This process is repeated many times until the network achieves a satisfactory level of accuracy. Let's say we want to train a neural network to recognize whether an image contains a cat. We would provide the network with a set of images, some with cats and some without. Each image would be labeled accordingly. The network would analyze features within the images, such as edges, shapes, and colors. Based on these features and their combinations, it would make a guess cat or not cat. Initially, the network's guesses would be random. However, with each correct guess, it would strengthen the connections that led to that guess. Conversely, with each incorrect guess, it would weaken the connections responsible. Through this iterative process of trial and error, the neural network would gradually learn to identify the features that are most indicative of a cat. Eventually, it would become quite accurate at distinguishing cat images from non-cat images, even if those images were completely new to it. This ability to generalize to unseen data is a key strength of neural networks.